From the moment we first gaze upon a starlit sky, a profound question stirs within us. What is this universe we find ourselves in? It's a question that has echoed through the ages, pondered by philosophers, scientists, and dreamers alike. The vastness above inspires awe and a sense of wonder that transcends the boundaries of language. We are but tiny beings on a small planet, yet the cosmos calls to us, beckoning us to explore its mysteries. The stars have served as our guides, our storytellers, and our constant companions in the vast cosmic expanse. As we've built telescopes and launched probes, our understanding of the universe has grown, but with each discovery, new questions emerge. The more we learn, the more we realize how much more there is to know. In 1990, the Voyager 1 spacecraft turned its camera back towards Earth from about 3.7 billion miles. The resulting image, known as the pale blue dot, shows Earth as a tiny point of light. This iconic photograph reminds us of our place in the grand scheme of things. From such a distance, Earth appears as a fragile speck of dust in the vast cosmic desert. On that tiny dot, all of human history has unfolded. It's a humbling perspective, highlighting the preciousness of our home planet. The image underscores the interconnectedness of all things. The same physical laws that govern the universe apply to us here on Earth. The atoms that make up our bodies are the same atoms that form distant stars. We are a part of the universe, and it is a part of us. Looking at the pale blue dot, it's easy to feel small and insignificant, but we should also feel a sense of awe and wonder. The fact that we exist at all on this tiny planet is miraculous. We are the product of billions of years of cosmic evolution. That in itself is something to celebrate. To fully grasp the vastness of the universe, it's helpful to consider our cosmic address, starting with our home planet, Earth. We inhabit a rocky planet, the third from our Sun, located in a spiral arm of the Milky Way galaxy. The Milky Way, in turn, is just one of billions of galaxies scattered throughout the observable universe. Imagine our cosmic address as a series of nested spheres, each encompassing a larger scale of the universe. Within our solar system, we find planets, moons, asteroids, and comets, all bound to the gravitational influence of our Sun. Venturing further out, we encounter vast clouds of interstellar gas and dust, the remnants of exploded stars and the birthplaces of new ones. Beyond our galaxy lies a realm of galactic clusters, superclusters, and cosmic voids, structures so vast that they challenge our very understanding of scale. The observable universe, the portion we can currently detect, spans tens of billions of light years, and it's constantly expanding, and yet, this may only be a tiny fraction of the entire universe, which could extend infinitely in all directions. The sheer scale of the universe can be overwhelming, but it's also a source of endless fascination. Every point of light we see in the night sky represents a distant sun, perhaps orbited by its own system of planets. And on some of those planets, who knows what wonders might exist? The possibilities are as limitless as the universe itself. The human spirit is inherently curious. We are driven to explore, to understand, and to find our place in the grand scheme of things. Our fascination with the universe is a testament to this innate curiosity, this desire to unravel the mysteries that surround us. From the earliest cave paintings of celestial objects to the latest space probes exploring the outer solar system, we have always sought to comprehend the cosmos. Throughout history, our understanding of the universe has been shaped by both scientific discoveries and philosophical inquiries. Ancient civilizations developed elaborate cosmologies, often intertwined with their myths and religions. With the advent of modern science, we began to develop a more empirical understanding of the universe, based on observation, experimentation, and mathematical models. Yet, even as our scientific knowledge has advanced, many fundamental questions remain unanswered. What is the ultimate fate of the universe? Are we alone in the cosmos? What is the nature of time and space? These questions continue to challenge our assumptions and inspire us to push the boundaries of human knowledge. The pursuit of these answers is not merely an intellectual exercise, it has practical implications for our future as a species. By understanding the universe, we can better understand ourselves and our place within it. We can learn to harness the resources of space, protect our planet from cosmic hazards, and perhaps even discover new forms of life beyond Earth. Section 5. A journey begins. This video is an invitation to embark on a journey of cosmic exploration, a quest to unravel the mysteries of the universe and our place within it. Together we will delve into the depths of space and time, exploring the wonders of the cosmos and grappling with the profound questions that they raise. Our journey will take us from the smallest subatomic particles to the largest structures in the universe, from the birth of stars to the collision of galaxies, from the nature of time to the possibility of life beyond Earth. Along the way, we will encounter awe-inspiring sights, mind-bending concepts, and humbling truths. We will confront the limits of our current understanding and explore the frontiers of scientific inquiry. But most importantly, we will be reminded of the incredible beauty, complexity, and wonder of the universe we inhabit. So, fasten your seatbelts and prepare to have your mind blown. Our journey into the heart of the universe is about to begin. Section 1. Island universes. For centuries, astronomers could only marvel at fuzzy patches of light scattered across the night sky, known as nebulae. It wasn't until the early 20th century that the true nature of these objects was revealed. They were not clouds of gas within our own galaxy, but vast, distant island universes, each containing billions of stars. This realization revolutionized our understanding of the universe's scale and structure. These island universes, now known as galaxies, come in a variety of shapes and sizes. Some, like our own Milky Way, are spiral galaxies, with graceful arms of stars and gas swirling around a central bulge. Others are elliptical galaxies, smooth and oval-shaped, while still others are irregular galaxies, lacking any defined structure. Each galaxy is a vast collection of stars, gas, dust, and dark matter, all held together by the force of gravity. The distances between galaxies are immense, typically measured in millions of light-years. Yet despite their separation, galaxies are not isolated islands. They interact with each other through gravitational forces, sometimes colliding and merging in spectacular displays of cosmic fireworks. The discovery of galaxies beyond our own was a profound moment in astronomy. It expanded our cosmic horizons, revealing a universe far grander and more complex than previously imagined. It also raised new questions about the origin and evolution of galaxies, questions that continue to drive astronomical research today. Section 2. The Milky Way, our galactic home. Our solar system resides within the Milky Way galaxy, a barred spiral galaxy containing hundreds of billions of stars. From our vantage point within one of the Milky Way's spiral arms, we have a limited view of our galactic home, but astronomers have pieced together a remarkably detailed picture of its structure and evolution. The Milky Way is a vast, flattened disk of stars, gas, and dust, with a diameter of about 100,000 light-years. At its center lies a supermassive black hole, a region of intense gravity that binds the entire galaxy together. Spiral arms, like the one we inhabit, extend outward from the central bulge, tracing paths of star formation and galactic rotation. Our Sun, a relatively ordinary star, orbits the Milky Way's center at a distance of about 26,000 light-years, completing one orbit roughly every 230 million years. As we journey around the galaxy, we encounter other stars, gas clouds, and dust lanes, creating the ever-changing tapestry of the night sky. The Milky Way is not a static island universe. It is constantly evolving, with new stars being born in stellar nurseries and old stars ending their lives in supernova explosions. The galaxy's spiral arms are shaped by density waves that propagate through the galactic disk, triggering bursts of star formation. Stars are not eternal objects. They have a life cycle, just like living organisms. They are born in vast clouds of gas and dust, known as stellar nurseries, scattered throughout galaxies. These nurseries are regions of intense star formation, where gravity pulls together clouds of interstellar material, triggering the birth of new stars. The process of star formation begins when a cloud of gas and dust becomes gravitationally unstable. This can be triggered by a variety of factors, such as the shock wave from a nearby supernova explosion, or the passage of a spiral arm density wave. As the cloud collapses, it begins to heat up and rotate, forming a protostar at its center. The protostar continues to accrete material from the surrounding cloud, growing in mass and temperature. Eventually, the core of the protostar becomes hot and dense enough to ignite nuclear fusion, the process that powers stars. At this point, the protostar becomes a true star, radiating energy into space and illuminating its surroundings. Star formation is a continuous process, with new stars being born in stellar nurseries throughout the universe. These stellar nurseries are not only the birthplaces of stars but also the sites of planet formation, as disks of gas and dust around young stars coalesce into planets. Once a star ignites nuclear fusion in its core, it embarks on a long and fascinating life cycle, the duration and characteristics of which depend primarily on its mass. Massive stars live fast and die young, while low-mass stars, like our Sun, can shine for billions of years. During its main sequence phase, a star fuses hydrogen into helium in its core, releasing energy in the form of light and heat. This process creates outward pressure that balances the inward pull of gravity, maintaining the star's stability. The main sequence phase is the longest stage in a star's life, lasting for about 90% of its total lifespan. As a star ages, it gradually consumes the hydrogen fuel in its core. Eventually, the core runs out of hydrogen, and the star begins to evolve off the main sequence. The star's core contracts and heats up, while its outer layers expand and cool, transforming the star into a red giant. The fate of a red giant depends on its mass. Low-mass stars, like our Sun, will eventually shed their outer layers, forming planetary nebulae and leaving behind their dense cores as white dwarfs. Massive stars, on the other hand, face a more dramatic end. When a star exhausts its nuclear fuel and can no longer support itself against gravity, it collapses under its own weight, leading to the formation of stellar remnants, white dwarfs, neutron stars, or black holes. These remnants are some of the densest and most extreme objects in the universe. White dwarfs are the remnants of low-mass stars like our Sun. They are incredibly dense, with a mass comparable to the Sun's crammed into a volume roughly the size of Earth. White dwarfs are supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same energy state. Neutron stars are the remnants of more massive stars. They are even denser than white dwarfs, with a mass greater than the Sun squeezed into a sphere only a few miles across. Neutron stars are supported by neutron degeneracy pressure, a similar quantum mechanical effect involving neutrons. Black holes are the most extreme stellar remnants formed when the core of a massive star collapses to a point of infinite density, known as a singularity. Black holes have such strong gravity that nothing, not even light, can escape their grasp. Section 6: Galaxies in Motion, Cosmic Expansion, and the Hubble Law. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that revolutionized our understanding of the universe. Galaxies are not stationary but are moving away from each other. And the farther away a galaxy is, the faster it is receding. This observation, known as Hubble's law, provided the first evidence that the universe is expanding. Hubble's discovery was based on his observations of the redshift of light from distant galaxies. Redshift is a phenomenon in which light waves are stretched as they travel through an expanding universe, causing their wavelengths to shift towards the red end of the electromagnetic spectrum. Just as the sound waves of a siren are stretched out and sound lower in pitch as an ambulance moves away from us, the light waves from receding galaxies are stretched out and appear redder. Hubble's law implies that the universe was once much smaller and denser than it is today. By extrapolating backward in time, cosmologists estimate that the universe began with a hot, dense state known as the Big Bang, about 13.8 billion years ago. The expansion of the universe is one of the most fundamental concepts in modern cosmology. It has profound implications for our understanding of the universe's origin, evolution, and ultimate fate. Section 7: Cosmic Collisions, the Dance of Galaxies. While galaxies are generally moving away from each other due to cosmic expansion, they also interact with each other through the force of gravity. These interactions can lead to a variety of spectacular events, including galactic collisions and mergers. Galactic collisions are not as violent as they might sound. Galaxies are mostly empty space, so when they collide, their stars rarely collide directly. Instead, the galaxy's gravitational fields interact. distorting their shapes and triggering bursts of star formation. Over millions of years, colliding galaxies can merge to form a single, larger galaxy. The Milky Way itself is thought to have undergone several mergers with smaller galaxies over its lifetime. In fact, our galaxy is currently on a collision course with the Andromeda galaxy, our nearest large galactic neighbor. In about 4 billion years, the two galaxies will begin to merge, creating a spectacular cosmic display visible from Earth. Galactic collisions are a natural part of galaxy evolution. They play a crucial role in shaping the distribution of galaxies in the universe and triggering the formation of new stars and planetary systems. Section 8. Active galaxies and quasars galactic engines. Not all galaxies are created equal. Some galaxies, known as active galaxies, harbor extremely luminous and energetic cores, powered by supermassive black holes at their centers. These galactic engines release vast amounts of energy across the electromagnetic spectrum, from radio waves to gamma rays. Quasars, the most luminous type of active galaxy, are among the most distant and energetic objects in the universe. They are thought to be powered by supermassive black holes billions of times more massive than our Sun. As matter falls into a quasar's central black hole, it forms an accretion disk, a swirling disk of gas and dust heated to millions of degrees. This superheated material emits intense radiation, making quasars visible across vast cosmic distances. Active galaxies and quasars provide insights into the extreme physics at play near supermassive black holes. They also offer a glimpse into the early universe, as they are often found at great distances, corresponding to earlier epochs in cosmic history. Section 9. The Cosmic Web, large-scale structure of the universe. On the largest scales, the universe is not a random scattering of galaxies but is organized into a vast and intricate cosmic web. This web-like structure consists of filaments, sheets, and voids, with galaxies clustered along the filaments and in the intersections of filaments. The cosmic web is thought to have originated from tiny density fluctuations in the very early universe. These fluctuations, amplified by gravity over billions of years, gave rise to the large-scale structure we observe today. The filaments of the cosmic web are like rivers of galaxies, channeling the flow of matter and shaping the distribution of galaxies throughout the universe. Understanding the cosmic web is crucial for understanding the evolution of the universe and the formation of galaxies. By studying the distribution of galaxies and the properties of the cosmic web, cosmologists can test their models of the universe's origin and evolution. Section 10. Dark matter, the invisible hand. Astronomers have long observed that galaxies rotate faster than they should based on the visible matter they contain. This discrepancy suggests that there must be some invisible form of matter, dubbed dark matter, providing the extra gravity to hold galaxies together. Dark matter does not interact with light, making it invisible to telescopes. However, its gravitational effects can be inferred from its influence on the rotation of galaxies, the motion of galaxies within clusters, and the bending of light around massive objects. The nature of dark matter remains one of the biggest mysteries in modern astrophysics. Scientists believe it is composed of some yet undiscovered particle that interacts very weakly with ordinary matter. Identifying the nature of dark matter would be a major scientific breakthrough, providing insights into the fundamental building blocks of the universe. Section 11. Dark energy, the accelerating universe. In the late 1990s, astronomers made another surprising discovery that shook the foundations of cosmology. The expansion of the universe is not slowing down, as expected due to gravity, but is actually accelerating. This unexpected finding implies the existence of a mysterious force, dubbed dark energy, that counteracts gravity on cosmic scales. Dark energy is thought to make up the majority of the universe's energy density, dwarfing the contributions from both ordinary matter and dark matter. However, its nature and origin remain enigmatic. One possibility is that dark energy is a property of space itself, a kind of cosmological constant that exerts a negative pressure, driving the acceleration of the universe. Another possibility is that our understanding of gravity is incomplete, and that a modified theory of gravity is needed to explain the observed acceleration. The discovery of dark energy has profound implications for our understanding of the universe's fate. If dark energy continues to dominate the universe's expansion, it will eventually drive all galaxies except those in our local group beyond our cosmic horizon, leaving us in an increasingly isolated and dark universe. To understand the universe we live in today, we must look back to its earliest moments. The Big Bang theory describes the universe's evolution from an extremely hot, dense state about 13.8 billion years ago. In the first fraction of a second after the Big Bang, the universe was a seething cauldron of elementary particles and energy. As the universe expanded and cooled, protons and neutrons formed from quarks, and these particles combined to form the first atomic nuclei, primarily hydrogen and helium. For hundreds of thousands of years, the universe was filled with a hot, dense plasma of protons, electrons, and photons. As the universe continued to expand and cool, electrons combined with protons to form neutral hydrogen atoms, an event known as recombination. This transition allowed photons to travel freely through space, marking the beginning of the cosmic dark ages. The early universe was a time of rapid change and evolution, setting the stage for the formation of stars, galaxies, and the large-scale structure we observe today. One of the most compelling pieces of evidence supporting the Big Bang theory is the cosmic microwave background, CMB, radiation. This faint afterglow of the Big Bang was discovered in 1965 and has been studied in great detail ever since. The CMB is a faint microwave radiation that permeates all of space. It is the remnant of the hot, dense plasma that filled the early universe, redshifted to microwave wavelengths by the expansion of the universe. The CMB provides a snapshot of the universe as it was about 380,000 years after the Big Bang. Tiny temperature fluctuations in the CMB reflect density variations in the early universe, the seeds of the large-scale structure we observe today. Studying the CMB provides cosmologists with a wealth of information about the early universe, including its age, composition, and geometry. It is a cornerstone of modern cosmology and a testament to the power of scientific inquiry to probe the universe's deepest secrets. Time is one of the most fundamental aspects of our existence. It is the medium through which we experience change and the framework within which we organize our lives. From the regular ticking of a clock to the changing seasons, time is a constant presence. Yet, despite its ubiquity, the concept of time is surprisingly elusive and complex. Philosophers, scientists, and thinkers throughout history have grappled with the nature of time. Is it a continuous flow, like a river, or a series of discrete moments, like beads on a string? Does time have a beginning and an end, or is it infinite? These questions have sparked profound debates and continue to intrigue us today. In physics, time is often regarded as the fourth dimension alongside the three spatial dimensions. This perspective allows us to describe the position and movement of objects in a four-dimensional space-time continuum. The flow of time, however, seems to be unidirectional. We move from the past to the present and into the future, but never in reverse. Our understanding of time has profound implications for our worldview. It influences everything from the way we conduct science and understand the universe to our daily routines and long-term planning. As we delve deeper into the nature of time, we uncover layers of complexity that challenge our perceptions and expand our horizons. Section 2. Historical Perspectives on Time. The human understanding of time has evolved significantly over millennia. Ancient civilizations used natural cycles, such as the phases of the moon and the changing seasons, to mark the passage of time. These early timekeeping methods were crucial for agricultural societies, helping them to determine planting and harvesting seasons. The ancient Egyptians were among the first to develop a more sophisticated understanding of time, creating calendars based on the solar year. They also invented the sundial, which allowed them to measure time during the day more precisely. Sundials divided daylight into 12 parts, leading to the concept of hours. In ancient Greece, philosophers like Aristotle and Plato pondered the nature of time. Plato viewed time as a moving image of eternity, a concept rooted in his philosophical framework. Aristotle, on the other hand, saw time as a measure of change intrinsically linked to the motion of objects and events. The advent of mechanical clocks in medieval Europe marked a significant leap in timekeeping technology. These clocks allowed for the more precise measurement of hours and minutes, revolutionizing daily life and paving the way for modern timekeeping. The invention of the pendulum clock in the 17th century by Christian Huygens further improved accuracy, influencing scientific research and navigation. Section 3. Time in Physics, Newton versus Einstein. The scientific understanding of time underwent a dramatic transformation with the work of Isaac Newton and Albert Einstein. Newton's classical mechanics, formulated in the 17th century, treated time as an absolute and universal entity, flowing at a constant rate independent of the observer. In this view, time was a backdrop against which events unfolded and the motion of objects could be described. Newton's concept of absolute time dominated scientific thought for centuries, providing a solid foundation for the laws of motion and gravity. However, this view was fundamentally challenged in the early 20th century by Albert Einstein's theory of relativity, which introduced a revolutionary perspective on time. Einstein's theory of special relativity revealed that time is not absolute but relative, depending on the observer's state of motion. According to special relativity, time can stretch or contract based on the relative velocities of observers. This phenomenon, known as time dilation, shows that time is intertwined with space to form a four-dimensional continuum called spacetime. Einstein's general theory of relativity further expanded this concept by demonstrating that time is affected by gravity. Massive objects, such as planets and stars, warp the fabric of spacetime, causing time to slow down in their vicinity. This curvature of spacetime explains the orbits of planets and the bending of light around massive bodies, revolutionizing our understanding of the cosmos. Section 4. The Arrow of Time. One of the most intriguing aspects of time is its apparent directionality, often referred to as the arrow of time. Unlike the spatial dimensions, which are symmetrical and direction-independent, time seems to flow in a single direction, from the past to the future. This unidirectional flow is a fundamental aspect of our experience and understanding of the world. The arrow of time is closely related to the concept of entropy, as described by the second law of thermodynamics. Entropy measures the degree of disorder or randomness in a system. The second law states that the total entropy of an isolated system can never decrease over time. It either increases or remains constant. This principle is often summarized by the idea that natural processes tend to move from order to disorder. This increase in entropy provides a thermodynamic explanation for the arrow of time. For example, a cup of hot coffee left on a table will eventually cool down to room temperature, but it will never spontaneously heat up. This irreversible process reflects the natural tendency towards increased entropy. The arrow of time manifests in various ways, from the macroscopic level of everyday phenomena to the microscopic level of particle interactions. It governs the processes of aging, the evolution of the universe, and the progression of events. Despite its fundamental nature, the underlying reasons for the arrow of time remain a subject of ongoing scientific inquiry and philosophical debate. Section 5. Measuring time from sundials to atomic clocks. Throughout history, humans have invented various methods to measure time with increasing precision. The earliest timekeeping devices, such as sundials, relied on the apparent motion of the sun across the sky. Sundials divided daylight into hours, providing a simple yet effective way to track the passage of time during the day. The development of mechanical clocks in the Middle Ages marked a significant advancement in timekeeping. These clocks used gears and escapements to regulate the movement of hands on a dial, allowing for the measurement of hours and minutes. The invention of the pendulum clock by Christian Huygens in the 17th century greatly improved accuracy, reducing errors to mere seconds per day. The quest for even greater precision led to the development of atomic clocks in the 20th century. Atomic clocks use the vibrations of atoms, typically cesium or rubidium, to measure time with extraordinary accuracy. They are capable of maintaining time to within a billionth of a second per day, making them the standard for international timekeeping. Atomic clocks are essential for various modern technologies, including GPS navigation, telecommunications, and scientific research. They provide the basis for coordinated universal time, the time standard used worldwide. The precision of atomic clocks allows for highly accurate time synchronization across the globe, enabling the smooth operation of complex technological systems. Section 6. Time dilation. Einstein's relativity. Einstein's theory of relativity introduced the concept of time dilation, a phenomenon that dramatically alters our understanding of time. Time dilation occurs when the passage of time is affected by the relative velocity between observers or by the presence of strong gravitational fields. This effect, though counterintuitive, has been confirmed by numerous experiments and observations. In special relativity, time dilation is a consequence of the fact that the speed of light is constant for all observers, regardless of their relative motion. As a result, an observer moving at a high velocity relative to another will experience time more slowly. This means that a clock moving at a significant fraction of the speed of light will tick more slowly than a stationary clock. General relativity extends this concept to include the effects of gravity. According to general relativity, time passes more slowly in stronger gravitational fields. This phenomenon, known as gravitational time dilation, means that a clock placed near a massive object like a planet or a star will tick more slowly than a clock further away. Time dilation has practical implications for modern technology. For example, the global positioning system relies on precise time measurements from satellites orbiting the Earth. These satellites experience both relative motion and differences in gravitational potential compared to the Earth's surface. To ensure accurate positioning, the effects of time dilation must be accounted for in the system's calculations. Section 7. Time travel, fiction and theoretical physics. Time travel has long captured the human imagination, inspiring countless works of fiction and speculative thought. From H.G. Wells' The Time Machine to modern science fiction films, the idea of traveling through time, either to the past or the future, has fascinated us. But is time travel possible within the framework of our current understanding of physics? Einstein's theory of relativity provides some intriguing possibilities for time travel. One theoretical concept is the wormhole, a hypothetical tunnel through space-time that could connect distant points in space and time. If such wormholes exist, they could potentially allow for travel between different times as well as different locations in the universe. Another concept is time dilation, which could enable a form of one-way time travel to the future. For example, an astronaut traveling at near light speeds or spending time in a strong gravitational field would experience time more slowly than someone on Earth. Upon returning, the astronaut would find that more time had passed on Earth than they had experienced, effectively traveling into the future. However, time travel to the past presents significant challenges and paradoxes. The grandfather paradox, for example, raises the question of what would happen if a time traveler went back and prevented their own grandfather from meeting their grandmother, thus preventing the time traveler's own existence. These paradoxes suggest that backward time travel may be impossible or subject to unknown constraints. Section 8. Cosmic time, the age of the universe. Understanding the age of the universe is a crucial aspect of cosmology, providing insights into its origin and evolution. The prevailing cosmological model, known as the Big Bang theory, posits that the universe began as an extremely hot and dense state about 13.8 billion years ago and has been expanding ever since. Determining the age of the universe involves several lines of evidence. One key piece of evidence comes from observing distant galaxies and measuring their redshifts, which indicate that the universe is expanding. By extrapolating this expansion backward in time, cosmologists can estimate the age of the universe. Another important piece of evidence comes from the cosmic microwave background or CMB radiation, the faint afterglow of the Big Bang. The CMB provides a snapshot of the universe as it was about 380,000 years after the Big Bang. By studying the properties of the CMB, cosmologists can infer the age and composition of the universe. The study of globular clusters, dense groups of ancient stars, also provides age estimates for the universe. These clusters contain some of the oldest known stars, and by calculating their ages, scientists can place lower bounds on the age of the universe. Section 9. Entropy and the second law of thermodynamics. Entropy, a measure of disorder or randomness in a system, plays a crucial role in our understanding of time and its directionality. The second law of thermodynamics states that in any closed system, the total entropy can never decrease over time. It either increases or remains constant. This principle underlies the arrow of time, giving it a thermodynamic foundation. In everyday terms, the second law explains why certain processes are irreversible. For example, a broken egg cannot spontaneously reassemble itself, and a cup of hot coffee will eventually cool to room temperature, but will not heat up on its own. These processes reflect the natural tendency for systems to move towards greater entropy. On a cosmic scale, the second law of thermodynamics has profound implications for the fate of the universe. As the universe expands, its total entropy increases. Over billions of years, the universe will continue to evolve towards a state of maximum entropy, known as heat death, where all energy is evenly distributed and no thermodynamic processes can occur. The concept of entropy also intersects with information theory, where it is related to the amount of information needed to describe a system's state. This connection has led to intriguing insights into the nature of black holes, where the entropy of a black hole is proportional to the surface area of its event horizon rather than its volume. Section 10. Psychological time, how we perceive time. Our perception of time is deeply intertwined with our consciousness and mental processes. Psychological time, or subjective time, refers to how we experience the passage of time, which can vary significantly depending on various factors such as attention, emotion, and age. For instance, time often seems to fly when we are engaged in enjoyable activities, while it drags during periods of boredom or stress. This phenomenon is related to the amount of information our brains process. Engaging activities typically involve more cognitive processing, making time feel shorter in hindsight. Emotions also play a crucial role in our perception of time. Strong emotions, whether positive or negative, can alter our sense of time. For example, moments of fear or excitement can make time seem to slow down, a phenomenon often reported during life-threatening situations. Age is another factor that influences our perception of time. As we grow older, time seems to pass more quickly. One theory suggests that this is because each year constitutes a smaller fraction of our total lived experience, making them feel shorter in comparison. Understanding psychological time provides valuable insights into human cognition and behavior. It helps explain why time management can be challenging and why our memories of events are often influenced by how we experience time during those events. Section 11. Biological time, circadian rhythms. Biological time refers to the internal processes that regulate the timing of various physiological functions in living organisms. One of the most well-known aspects of biological time is the circadian rhythm, a roughly 24-hour cycle that governs sleep-wake patterns, hormone release, and other essential bodily functions. Circadian rhythms are driven by an internal biological clock located in the hypothalamus of the brain. This clock is synchronized with the external environment through cues such as light and temperature. The presence of natural light helps regulate the release of melatonin, a hormone that promotes sleep. Disruptions to circadian rhythms can have significant impacts on health and well-being. For example, shift work, jet lag, and exposure to artificial light at night can lead to sleep disorders, metabolic issues, and other health problems. Maintaining regular sleep patterns and exposure to natural light can help keep circadian rhythms in sync. Circadian rhythms are not unique to humans. They are found in almost all living organisms, from plants to animals. In plants, circadian rhythms regulate processes such as photosynthesis and leaf movement. In animals, they influence behaviors such as feeding, mating, and migration. Research into circadian rhythms continues to uncover new insights into how biological time affects health and behavior. Understanding these rhythms can lead to better treatments for sleep disorders, improved work schedules, and strategies for enhancing overall well-being. Section 12. Philosophical views on time. Philosophical inquiries into the nature of time date back to ancient civilizations. Philosophers have long debated whether time is an objective reality, independent of human perception, or a construct of the mind. These debates have led to various perspectives on the nature of time and its implications for our understanding of the world. One of the key philosophical questions is whether time is absolute or relational. The absolutist view, associated with Newton, suggests that time exists independently of events and objects. In contrast, the relational view, supported by Leibniz and others, posits that time is a measure of the relationships between events and does not exist independently of them. Another significant debate revolves around the nature of the present. The A theory of time, or presentism, holds that only the present moment is real, and the past and future do not exist. The B theory of time, or eternalism, argues that past, present, and future events are equally real, and the flow of time is an illusion. Philosophical discussions also explore the implications of time for free will and determinism. If the future is already determined, as some theories suggest, it raises questions about the nature of human agency and the possibility of making free choices. The philosophical exploration of time enhances our understanding of its complexities and challenges our assumptions about reality. It encourages us to reflect on the fundamental nature of existence and our place within the temporal framework of the universe. Section 13. The future of time, speculations and theories. As our understanding of time continues to evolve, so do our speculations about its future. Advances in physics, cosmology, and technology offer new insights and possibilities for how we might perceive and interact with time in the future. One area of speculation involves the potential for time travel, a concept popularized by science fiction but grounded in theoretical physics. While practical time travel remains elusive, ongoing research into wormholes, quantum mechanics, and other phenomena may one day reveal new possibilities for manipulating time. The study of the universe's ultimate fate also raises questions about the future of time. Theories about the universe's end range from continued expansion and heat death to a potential Big Crunch or cyclic model. These scenarios have profound implications for the nature of time and its continuity. Technological advancements may also change how we measure and experience time. The development of more precise timekeeping devices, integration of time management tools with artificial intelligence, and exploration of virtual realities could transform our temporal experiences and interactions. Ultimately, the future of time is a subject of ongoing exploration and imagination. As we continue to push the boundaries of our understanding, new discoveries and technologies will undoubtedly shape our perception of time in ways we cannot yet fully anticipate. Our quest to understand why we exist has led to numerous scientific theories that attempt to unravel the mysteries of our origin and place in the universe. These theories span various fields, including cosmology, physics, and biology, each offering unique insights into our existence. One of the most influential scientific theories is the Big Bang theory, which describes the universe's expansion from an incredibly hot and dense state approximately 13.8 billion years ago. This theory provides a framework for understanding the origin of the universe and the formation of galaxies, stars, and planets, ultimately leading to the conditions necessary for life. Another critical theory is the theory of evolution by natural selection, proposed by Charles Darwin. This biological framework explains how life on Earth has diversified and adapted over billions of years. By understanding the mechanisms of evolution, we can trace the development of complex organisms, including humans, from simpler ancestral forms. In the realm of physics, the laws of thermodynamics and quantum mechanics offer insights into the fundamental nature of reality. These theories describe the behavior of matter and energy at both macroscopic and microscopic scales, shedding light on the processes that govern the universe. These scientific theories collectively contribute to our understanding of existence, providing a coherent narrative of how the universe and life as we know it have come to be. However, they also raise profound questions about the ultimate purpose and meaning of our existence. The anthropic principle is a philosophical consideration that attempts to explain why the universe's fundamental physical constants and laws appear finely tuned to support life. It suggests that the universe's properties are not just coincidental, but are somehow linked to the existence of observers like us. There are two main formulations of the anthropic principle: the weak anthropic principle, or WAP, and the strong anthropic principle, or SAP. The WAP asserts that the universe's properties must allow for the existence of observers because we are here to observe them. In other words, the universe's conditions are such that they permit life because life exists to observe those conditions. The SAP takes this idea further, proposing that the universe must have properties that inevitably lead to the emergence of intelligent life. Some interpretations of the SAP suggest that the universe is designed in such a way that life is not only possible, but is an essential outcome. Critics of the anthropic principle argue that it does not provide a scientific explanation, but rather a tautological statement. Nonetheless, it prompts intriguing discussions about the nature of the universe and our place within it. It raises questions about whether the universe is uniquely suited for life, or if multiple universes exist with varying properties, some of which may not support life. The multiverse hypothesis posits that our universe is just one of many universes that exist simultaneously, each with its own unique set of physical laws and constants. This concept emerges from several areas of theoretical physics, including cosmology, string theory, and quantum mechanics. One version of the multiverse hypothesis arises from the theory of cosmic inflation. According to this theory, the rapid expansion of the early universe could have led to the creation of multiple bubble universes, each with different properties. Our universe is just one bubble among many, each potentially having different fundamental constants and physical laws. String theory, which attempts to unify all fundamental forces and particles in a single framework, also suggests the existence of a multiverse. It proposes that there could be vast numbers of possible universes, each corresponding to different solutions of the equations governing string theory. Quantum mechanics offers another avenue for the multiverse hypothesis through the many worlds interpretation. This interpretation suggests that every quantum event leads to a branching of the universe into multiple parallel worlds, each representing a different outcome of the event. The multiverse hypothesis provides a potential answer to the question of why our universe appears finely tuned for life. If there are countless universes with varying properties, it is not surprising that at least one, like ours, has the right conditions to support life. However, the multiverse remains a highly speculative idea, with no direct empirical evidence to support it. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, has profoundly altered our understanding of reality. The strange and counterintuitive nature of quantum mechanics has led to various interpretations that challenge our classical notions of existence. One of the most famous aspects of quantum mechanics is the principle of superposition, which states that particles can exist in multiple states simultaneously until they are observed or measured. This idea is famously illustrated by Schrödinger's cat thought experiment, where a cat in a sealed box is simultaneously alive and dead until the box is opened. Another fundamental principle is quantum entanglement, where particles become interconnected in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. This phenomenon, which Einstein referred to as spooky action at a distance, suggests a deep interconnectedness in the fabric of reality. The measurement problem in quantum mechanics raises questions about the role of the observer in determining the outcome of quantum events. The Copenhagen interpretation, one of the most widely accepted interpretations, posits that the act of measurement collapses a particle's wave function, determining its state. These principles and interpretations of quantum mechanics suggest that reality at the quantum level is fundamentally different from our everyday experiences. They challenge our understanding of causality, locality, and the nature of existence itself, opening up new avenues for exploring the mysteries of the universe. The simulation theory posits that our reality might be an artificial simulation created by an advanced civilization or consciousness. This idea, popularized by philosopher Nick Bostrom, suggests that future technologies could become so advanced that creating highly realistic simulations of entire universes, including conscious beings, becomes possible. Bostrom's argument is based on three propositions. 1. Almost all civilizations at our level of technological development go extinct before reaching the capability to create such simulations. 2. If civilizations reach this level, they are not interested in creating simulations. Or 3. We are almost certainly living in a simulation if such simulations are possible and numerous. The simulation theory raises profound questions about the nature of reality and our place within it. If we are living in a simulation, it challenges our understanding of consciousness, free will, and the fundamental nature of existence. It also suggests that our universe's laws and constants could be designed by the creators of the simulation. While the simulation theory remains speculative, it has garnered attention from both philosophers and scientists. Some argue that aspects of our universe, such as the discrete nature of space and time, or the fine-tuning of physical constants, could be indicative of a simulated reality. Critics of the theory point out that it is difficult to test or falsify, making it more of a philosophical hypothesis than a scientific one. Nonetheless, the simulation theory continues to inspire debate and exploration into the nature of our existence. Philosophers have long grappled with the question of why we exist, offering various perspectives that explore the nature of reality, consciousness, and meaning. These philosophical inquiries provide a rich tapestry of ideas that complement scientific theories and cultural interpretations of our existence. One foundational question in philosophy is whether existence has an inherent purpose or meaning. Existentialist philosophers such as Jean-Paul Sartre and Albert Camus argue that life has no intrinsic meaning, and it is up to individuals to create their own purpose and values. This perspective emphasizes personal responsibility and the freedom to define one's existence. Another philosophical approach is metaphysical realism, which posits that there is an objective reality independent of human perception. This view contrasts with idealism, which suggests that reality is fundamentally shaped by the mind and consciousness. These differing perspectives raise questions about the nature of reality and the role of human perception in shaping our experience of the world. Phenomenology, a philosophical movement founded by Edmund Husserl, focuses on the structures of consciousness and the lived experience of individuals. Phenomenologists seek to understand how we perceive and interpret the world, exploring the interplay between subjective experience and objective reality. Philosophical perspectives on existence also delve into the nature of time, free will, and the self. These inquiries challenge us to reflect on our place in the universe and the fundamental nature of our existence, offering insights that complement and enrich our scientific understanding. Section 7, Existentialism, Finding Meaning in an Absurd Universe. Existentialism explores the individual's search for meaning in an absurd universe. Thinkers like Kierkegaard, Nietzsche, Sartre, and Camus delve into freedom, choice, and the human condition. Sartre's existentialism emphasizes that existence precedes essence. We create our identity through choices and actions. Camus explores the absurd, the conflict between our desire for meaning and the universe's indifference. In the myth of Sisyphus, Camus describes finding meaning in struggle. Existentialism challenges us to embrace freedom and responsibility, creating our own values. Section 8. Religious and spiritual views on existence. Religious and spiritual traditions offer diverse perspectives on why we exist, often rooted in the belief in a higher power or transcendent reality. These views provide a sense of purpose, meaning, and connection to something greater than ourselves. In many religious traditions, the question of why we exist is answered through the concept of creation. For example, in the Abrahamic religions, the belief in a divine creator is central. Eastern religions such as Hinduism and Buddhism offer different perspectives on existence. Buddhism focuses on the Four Noble Truths and the Eightfold Path to attain enlightenment. Indigenous traditions emphasize a deep connection to the natural world. While views vary, they share a common thread of seeking to understand life's deeper meaning. Section 9. Cultural interpretations of our purpose. Different cultures have developed their own unique interpretations of our purpose and place in the universe, reflecting their histories, values, and worldviews. These cultural narratives shape how communities understand existence and provide frameworks for making sense of life. In many indigenous cultures, the concept of interconnectedness is central to their worldview. For example, Native American traditions often emphasize the idea that humans are part of a larger web of life, with responsibilities to the natural world and future generations. This perspective fosters a sense of stewardship and reverence for the environment. In contrast, modern Western culture is often characterized by individualism and a focus on personal achievement. This worldview emphasizes the importance of self-fulfillment, autonomy, and the pursuit of one's passions and goals. The emphasis on individualism can lead to a search for personal meaning and purpose, often through career, relationships, and self-expression. Eastern cultures, such as those influenced by Confucianism, place a strong emphasis on social harmony, family, and community. The concept of filial piety in Confucian thought underscores the importance of respecting and honoring one's parents and ancestors. This cultural framework encourages individuals to find purpose and meaning through their roles and responsibilities within the family and society. Cultural interpretations of existence are dynamic and evolve over time, influenced by historical events, technological advancements, and interactions with other cultures. These narratives provide diverse perspectives on what it means to live a meaningful life, and how we can contribute to the well-being of our communities and the world. Section 10. The role of consciousness. Consciousness is one of the most profound and enigmatic aspects of our existence. It is the quality that allows us to experience the world, think, feel, and be aware of ourselves and our surroundings. The nature of consciousness has been a subject of intense philosophical, scientific, and spiritual inquiry for centuries. From a scientific perspective, consciousness is often studied through the lens of neuroscience and cognitive science. Researchers seek to understand how the brain produces conscious experience, exploring the neural correlates of consciousness and the mechanisms underlying perception, thought, and emotion. Philosophically, the hard problem of consciousness, as articulated by David Chalmers, addresses the challenge of explaining why and how subjective experiences arise from physical processes in the brain. This problem highlights the gap between our understanding of the brain's physical functions and our experience of being conscious. Spiritual and religious traditions often view consciousness as a fundamental aspect of existence, sometimes extending beyond the physical body. For example, Hinduism and Buddhism explore the nature of consciousness through practices such as meditation and mindfulness, aiming to achieve higher states of awareness and enlightenment. The study of consciousness raises profound questions about the nature of reality, the self, and the mind-body connection. It challenges us to consider what it means to be conscious beings and how our awareness shapes our experience of existence. Section 11. The search for extraterrestrial life. The question of whether we are alone in the universe is one of the most intriguing and profound inquiries in science and philosophy. The search for extraterrestrial life seeks to answer this question by exploring the possibility of life beyond Earth, whether in our solar system or on distant exoplanets. Astrobiology, the interdisciplinary science that studies the potential for life in the universe, combines elements of biology, chemistry, astronomy, and planetary science. Researchers investigate the conditions necessary for life, such as the presence of liquid water, suitable temperatures, and essential chemical elements. One of the most promising locations for finding extraterrestrial life is Mars, where evidence of past liquid water and organic molecules has been discovered. Missions such as NASA's Perseverance rover aim to explore the Martian surface and search for signs of ancient microbial life. Beyond our solar system, the discovery of exoplanets, planets orbiting other stars, has opened new possibilities for finding habitable worlds. The Kepler Space Telescope and other observatories have identified thousands of exoplanets, some of which lie within the habitable zone where conditions might support liquid water. The search for extraterrestrial life not only seeks to answer questions about our place in the universe, but also has profound implications for our understanding of life's origins and the potential for diverse forms of life. Whether or not we eventually discover extraterrestrial life, the quest itself inspires wonder and curiosity about the vastness and complexity of the cosmos. Section 12. The Future of Humanity, Prospects and Challenges. As we continue to explore the mysteries of existence, we must also consider the future of humanity and the challenges and opportunities that lie ahead. The future of our species is shaped by our actions, advancements in technology, and our ability to address global issues. One of the most pressing challenges is climate change, which poses significant threats to the environment, economies, and societies worldwide. Addressing this challenge requires collective action to reduce greenhouse gas emissions, transition to renewable energy sources, and adapt to the changing climate. Technological advancements such as artificial intelligence, biotechnology, and space exploration offer both opportunities and ethical dilemmas. AI has the potential to revolutionize industries and improve quality of life, but it also raises concerns about job displacement, privacy, and the ethical implications of autonomous systems. Biotechnology holds promise for medical advancements, including gene editing and personalized medicine, but it also presents ethical questions about genetic modification and the potential for unintended consequences. Space exploration continues to push the boundaries of human knowledge and capability. Missions to the Moon, Mars, and beyond could unlock new resources, inspire innovation, and foster international collaboration. The prospect of human colonization of other planets raises questions about our long-term survival and the ethical considerations of expanding our presence in the cosmos. The future of humanity is shaped by our ability to navigate these challenges and opportunities with wisdom, foresight, and a commitment to the well-being of all people and the planet. Despite our advancements in science, philosophy, and technology, the ultimate questions of our existence remain elusive. We find ourselves standing at the edge of the unknown, peering into the vast expanse of mysteries yet to be unraveled. The pursuit of answers propels us forward, yet the more we learn, the more we realize how much remains beyond our grasp. Embracing the unknown is not a sign of defeat, but a testament to our unyielding curiosity and resilience. As we conclude our exploration of the universe, we are left with a profound sense of awe and wonder. The cosmos, in its vastness and complexity, continues to challenge our understanding and ignite our imaginations. From the smallest subatomic particles to the largest galactic superclusters, the universe unfolds with breathtaking beauty. We have journeyed through the depths of space, witnessing the birth and death of stars, the intricate dance of celestial objects bound by gravity's invisible hand. We have delved into the nature of time, grappling with its elusive essence and its profound influence on our perception of reality, contemplating the mysteries of our own existence, exploring scientific theories, and cultural interpretations that seek to illuminate our place in the grand scheme of things. Throughout our exploration, we have encountered concepts that stretch the limits of human comprehension. We have confronted the vastness of the cosmos, the strangeness of quantum mechanics, and the mind-boggling implications of the Multiverse Hypothesis. Yet with each new discovery, our fascination with the universe only deepens. The cosmos beckons us to continue exploring, to keep asking questions, and to marvel at the intricate workings of the natural world. The pursuit of knowledge about the universe is not merely an intellectual exercise, it is a journey of self-discovery. By understanding the cosmos, we gain a deeper appreciation for our own existence, our place within the grand tapestry of the universe. We come to realize that we are not isolated observers but active participants in the unfolding cosmic drama. Throughout our exploration, we have encountered recurring themes that highlight the interconnectedness of space, time, and existence. The fabric of space-time, warped by gravity, shapes the evolution of the universe. The laws of physics govern the interactions of matter and energy, shaping the universe we observe. The arrow of time drives the universe from order to disorder. It governs the life cycles of stars and the formation of galaxies. Our existence is a testament to the intricate interplay of cosmic processes. The atoms in our bodies were forged in the hearts of long-dead stars. We are, quite literally, stardust. Understanding this connection instills a sense of humility and wonder. The vastness of the universe can be both humbling and awe-inspiring. From a cosmic perspective, our planet is but a tiny speck of dust orbiting an ordinary star. Yet within this seeming insignificance lies a profound truth. We are conscious beings capable of contemplating our place in the universe. We have developed tools and technologies that allow us to peer into the depths of space. Embracing the cosmic perspective allows us to transcend the limitations of our everyday lives and connect with something larger than ourselves. As much as we have learned about the universe, countless questions remain unanswered. The cosmos is a vast and mysterious realm, with many secrets yet to be revealed. Each new discovery raises more questions, pushing the boundaries of human knowledge. What is the ultimate fate of the universe? Will it expand forever or collapse in a big crunch? What is the nature of dark matter and dark energy? Are there other universes beyond our own? The nature of time continues to puzzle us. What is the true nature of time? Is it fundamental or emergent? Is time travel possible? How does our perception of time influence our experience? The question of why we exist remains profound. Science explains how life arose, but the ultimate purpose remains open. Philosophical and cultural narratives offer diverse perspectives. The unanswered questions motivate us to continue exploring. The pursuit of knowledge is an ongoing journey. In the face of the universe's vastness, it's natural to question the significance of our own existence. Are we merely insignificant specks of dust, or do our lives hold inherent meaning? Our exploration of the universe offers some compelling perspectives. The fact that we exist is a testament to the extraordinary chain of events that led to our emergence. The universe has given rise to life, consciousness, and the ability to question our place in the cosmos. We are the product of countless generations of stars forged in supernova explosions. The human capacity for wonder and curiosity is a testament to our unique place in the universe. We are the universe becoming aware of itself, capable of contemplating its own origins. Our exploration of the universe, time, and our existence does not end with this video. It is an ongoing journey, a continuous process of discovery and wonder. The James Webb Space Telescope, launched in 2021, promises to revolutionize our view of the universe. It will study the atmospheres of exoplanets for signs of life. On Earth, particle accelerators like the Large Hadron Collider probe the fundamental building blocks of matter. Experiments in quantum mechanics push the boundaries of our understanding of reality. The pursuit of knowledge is a collaborative endeavor. By sharing discoveries and working together, we explore the endless wonders of the cosmos. Throughout our journey, we have witnessed the extraordinary power of human curiosity. It is this innate drive to explore, to question, to understand. From the earliest stargazers who mapped the constellations to the modern-day scientists who probe the depths of space and time, our thirst for knowledge has been a defining characteristic of our species. Curiosity is the engine that drives scientific discovery. It compels us to ask why and how, to seek explanations for the phenomena we observe, and to develop theories that can explain the workings of the universe. It is through this relentless questioning that we have been able to piece together the story of the universe's evolution, from the Big Bang to the emergence of life on Earth. But curiosity is not limited to the realm of science. It is a fundamental human trait that extends to all aspects of our lives. It drives us to learn new skills, to explore different cultures, to connect with others, and to seek out new experiences. It is through curiosity that we grow, learn, and expand our understanding of ourselves and the world around us. In a world often dominated by practicality and routine, it is essential to nurture our sense of wonder and curiosity. By embracing our innate thirst for knowledge, we keep our minds open to new possibilities, foster a sense of awe and appreciation for the world around us, and inspire future generations to continue exploring the mysteries of the universe. The universe is full of wonders waiting to be uncovered, and it is through the power of human curiosity that we will continue to unravel its secrets and deepen our understanding of our place within it. As we contemplate the vastness of the universe and the interconnectedness of all things, we are reminded of our responsibility as cosmic citizens. We are part of a vast and intricate web of life. Our actions have consequences for the future of life in the universe. We must care for our planet and reduce our impact on the environment. Climate change, pollution, and resource depletion threaten Earth's ecosystems. We have a moral obligation to address these challenges. Preserve the planet for future generations. Our actions have implications beyond Earth. As we venture into space, we must do so responsibly. Protect potential extraterrestrial life forms. Ensure our exploration benefits all of humanity. Foster peace, understanding, and cooperation among all people. Work together to address global challenges and promote social justice. Embrace our responsibility as cosmic citizens. Acknowledge our interconnectedness with the universe. Live in a way that honors the interconnectedness of all things. As we look to the future, we are filled with a sense of both excitement and uncertainty. The universe is constantly evolving, and so too is our place within it. Technological advancements, scientific discoveries, and cultural shifts continue to shape our understanding of the cosmos and our potential as a species. The 21st century has already witnessed remarkable progress in our exploration of the universe. We have landed rovers on Mars, sent probes to the outer reaches of our solar system, and detected thousands of exoplanets orbiting distant stars. The James Webb Space Telescope, launched in 2021, promises to revolutionize our view of the cosmos, peering deeper into space and time than ever before. Advances in artificial intelligence, biotechnology, and nanotechnology have the potential to transform our lives in profound ways, offering solutions to global challenges and enhancing human capabilities. However, these technologies also present ethical dilemmas and potential risks that we must carefully consider. The future of humanity is not predetermined, but rather something we create through our choices and actions. We have the power to shape our destiny, to create a future that is both prosperous and sustainable, and to ensure that the legacy we leave behind is one of peace, understanding, and progress. By embracing our curiosity, fostering our creativity, and working together, we can navigate the challenges and opportunities that lie ahead and create a future filled with possibilities for ourselves, our planet, and the generations to come. Despite our advancements, the universe retains its sense of mystery and wonder. Countless questions remain unanswered. The ultimate origins of the universe, the nature of consciousness, and the existence of extraterrestrial life captivate our imaginations. The unknown should be embraced as a source of inspiration. It drives us to explore, to question, and to seek deeper understanding. There is always more to learn, more to discover. The universe is a vast and complex tapestry. Our journey of exploration will continue. New insights will further illuminate the mysteries of the cosmos. Let us carry a sense of humility, wonder, and a thirst for knowledge. The universe is a gift, a source of endless fascination. Let us continue to explore its mysteries and celebrate its beauty. The journey is far from over, and the greatest discoveries may yet